This video is going to be a review of some basic ideas in trigonometry. Because trigonometry is a pretty big subject, we're going to limit it to just a few key ideas. So we're going to talk about right triangle trigonometry, and we're going to talk about the unit circle, but I'm not going to try to talk about where trigonometry is used or things like trigonometric identities. So let's start with the idea of what is trigonometry. It arises, at least historically, from studying right triangles. So let's think about what most people remember about trigonometry. Most people come into college thinking about this little acronym that they see in high school, SO-CA, TOA. And that's certainly not wrong, though it's probably a pretty incomplete conception of trigonometry. So what that thing tends to mean to a lot of students is that if you want to know the sine of an angle, let's say our angle is named theta, if you want to know the sine of theta, it's the length of the opposite side divided by the length of the hypotenuse. If you want to know the cosine of an angle theta, you need to do the length of the adjacent side divided by the length of the hypotenuse. And that all is helpful to know, but it is probably even more helpful to start with a little bit of context. So what's the context? First of all, we need to have a right triangle, which we have here. We have a 90-degree angle. And when we talk about things like opposite side and hypotenuse, we have to all remember that the hypotenuse is this side that's opposite of the right angle. And then you start with some angle, and the opposite side in this case is the side that's opposite of it on the triangle, whereas the adjacent side is this one that's right next to it. So with all that in mind, now we can start thinking about this example. So if you want to know what's the sine of 30 degrees, well, it's the length of the opposite side divided by the length of the hypotenuse. So that's going to be 1.5 divided by 3. And 1.5 divided by 3 is 1/2. So that's 0.5. If you wanted to know the cosine of 30 degrees, what would that be? Well, the cosine of 30 is going to be, it's the length of the adjacent side divided by the length of the hypotenuse. So 2.598 divided by 3, and that simplifies to be about 0.866. So the cosine of 30 is 0.866, and the sine of 30 is about 0.5. Now we're going to do the same kind of thing, but with a slightly bigger or smaller triangle. You can see that this triangle is bigger than the one on the last page, but it still contains a 30-degree angle, and it's still a right triangle. So let's ask, what's the cosine of 30 degrees? Well, the cosine of 30 degrees is, again, the length of the adjacent side divided by the length of the hypotenuse. So that's going to be 4.33 divided by 5. And similarly, the sine of 30 degrees is the length of the opposite side divided by the hypotenuse. That's going to be 2.5 divided by 5. And sometimes in mathematics, we don't get too bent out of shape about simplifying things extensively, but here it's kind of nice to do that, because if you simplify 4.33 divided by 5, you end up with 0.866, and if you simplify 2.5 divided by 5, you end up with 1/2. And it's absolutely no coincidence. These are the exact same numbers that we got on the other page. Even though this triangle is bigger, the idea is that if we're looking at ratios of lengths of sides, we end up with the same answers. We get 0.866 and we get 0.5, which are the same things we got for the cosine and sine of 30 degrees on the last page. We could do the same thing with a somewhat smaller triangle, still having a 30-degree angle and still being a right triangle. So we could look at the cosine of 30 degrees, and in this case, it looks like it's 1.732 divided by 2. And guess what that simplifies to? It simplifies to 0.866. And then similarly, we could do the sine of 30 degrees, which is going to be 1 divided by 2. And of course, that's 0.5, just as it was before. So you can see that if you just enlarge or shrink a right triangle but keep all the angles the same, you're going to end up with ratios of sides that do not change. And in fact, what we're going to see on the next page is that sometimes it makes a lot of sense to just use the right triangle that has the most convenient hypotenuse. And for us, the most convenient hypotenuse is often going to be a hypotenuse whose length is, instead of 2 or 3 or 5, we're going to use a length of 1. So you now see something that's virtually the same triangle, except it's been shrunk. It's got a hypotenuse of 1, and when we compute the cosine of 30 degrees, it's particularly easy now because it's the length of the adjacent side divided by the length of the hypotenuse. But since the hypotenuse has a length of 1, this 0.866 divided by 1 is just 0.866. So when your hypotenuse has a length of 1, the cosine is just staring you in the face. Similarly, what's the sine of 30 degrees? Well, it looks like it'd be 0.5, the length of the opposite side, divided by 1, the length of the hypotenuse. But again, that's just 0.5. So we see that when our hypotenuse has a length of 1, the sine of our angle is just looking right at us. So the sine and cosine are very easy to compute. When the hypotenuse has a length of 1, you don't even really have to do that division because you're just dividing by 1. Here's one more example, just to see how this works a little bit more. Let's imagine that we're interested in computing the cosine of 45 degrees. We can use either of these two triangles that we see here. I'll start by using the big one. If I want to compute the cosine of 45 degrees, well, officially, I should do the adjacent side divided by the hypotenuse. So that's going to be 2.121 divided by 3. And of course, if you actually plug that into a calculator and figure out what that division is, it's going to come out to 0.707. And that shouldn't be surprising at all, because over here we see a very similar looking triangle. In fact, it's officially called a similar triangle, or these two are similar triangles. And the idea is that if you use this smaller triangle to compute the cosine of 45 degrees, you would get 0.707 divided by 1, which is just 0.707. We could also compute the sine of 45 degrees. What would the sine of 45 degrees be? It would be 2.121 divided by 3. And of course, if you actually do that on a calculator, you're going to get 0.707, which is exactly what we expect over there. And in addition to just sort of seeing that these two triangles give consistent results, it's also good to notice that because we have a 45-degree angle, there's a certain amount of symmetry in this triangle. In fact, you can see that this angle up here at the top is also 45 degrees. And so it's not at all surprising that the sine and cosine of a 45-degree angle are the same. There are a couple of types of right triangles that show up really frequently in trigonometry, and many students feel like they need to memorize everything about those triangles. And it doesn't hurt to memorize them, but it's actually a good idea to sort of understand where these ideas come from. So let's say that we have a 45, 45, 90 right triangle like this one. And let's say that the hypotenuse is 1. You'd get a similar answer if the hypotenuse were 5 or 10. And you want to know, what is the sine of 45, or what is the cosine of 45? The thing to do is just label these other sides. So this side right here, let's call that A. And my first thought would be to call this side B, and then use the Pythagorean theorem. But before I even get into that, I want to point out that the symmetry of this triangle means that we can label it with the same letter A. And now the Pythagorean theorem says that a squared plus a squared is equal to 1 squared. And if we write that in a simpler way, we get 2 times a squared is equal to 1. And that tells us that a squared is equal to 1/2. And that tells us that a is equal to the square root of 1/2. There are a lot of ways you can write that. one really simple way is you can write 1 divided by the square root of 2. Another thing you can do if you want is you can rationalize the denominator by putting a square root of 2 down there and a square root of 2 up there. And then this thing becomes the square root of 2 divided by 2. So the point is we've found the value of a, it's square root of 2 divided by 2, and that was equal to 0.707 when we saw it on the other page. So the point here is that the cosine or sine of 45 degrees is equal to the square root of 2 divided by 2. And for the record, it's actually better to write the square root of 2 over 2 than it is to write 0.707, because 0.707 is just an approximation, but the square root of 2 over 2 is exact. Here's another pretty famous right triangle. It's the 30, 60, 90 right triangle. And admittedly, you can look at this picture and say you don't really see a 30, 60, 90 right triangle. What you see is a equilateral triangle. I should have said an equilateral triangle. All the angles are 60 degrees. And that's certainly true, but if you get out your scissors, you can easily turn this thing into a couple of 30, 60, 90 right triangles, and that's what I'm going to do. So now we have a 90-degree angle, and we have a 30-degree angle, and we want to know what are all these side lengths. Well, because trigonometry allows us to enlarge or shrink a triangle to a size that we like, it's pretty typical to start with a triangle whose hypotenuse is 1. So we're going to do that. We're going to label this side 1, just like this side is 1, and in fact this bottom side is 1. And that means that when we label this length, we know exactly what that is. It's just half of the bottom side, so that's 1/2. And now what we have is a right triangle with a hypotenuse of 1. It's got another side whose length is 1/2, and it's got a missing side whose length we don't know. That's this vertical piece right here. Let's call that B. And now we have a right triangle with sides of length 1/2 and B and 1. And so the Pythagorean theorem says that 1/2 squared plus B squared equals 1 squared. And that tells us that 1/2 squared, which is a fourth, 1/4 plus B squared is equal to 1. And of course that means B squared is equal to 3/4. So B squared is 3/4. And that means that B is equal to the square root of 3/4. And you can certainly write this square root of 3/4, but it's actually more helpful to write B equals square root of 3 divided by 2. That's just a little bit easier to plug into the calculator. So we now know that this blue length is square root of 3 divided by 2, and that makes it pretty easy to compute sines and cosines. So for instance, what's the cosine of 60 degrees? Cosine of 60 degrees is the adjacent side divided by the hypotenuse. So that's going to be 1/2 divided by 1. And I shouldn't really need to keep writing divided by 1. That's the whole point of using a triangle whose hypotenuse is 1. And then the sine of 60 degrees is going to be square root of 3 over 2. Technically, I need to divide by 1, but there's really no point in doing that. So I'm just going to write square root of 3 over 2. So the Pythagorean theorem, along with just a tiny bit of geometry, gives us the sine and cosine of 60 degrees. So what have we seen so far? We've seen that when you want to know the sine or cosine of an angle, you can use any right triangle you want that contains those angles, and it's particularly convenient to use a right triangle whose hypotenuse is 1. And then when you do that, the sine and cosine of your angles end up just being the sides of the legs of the right triangle. So in trigonometry, what we do is we kind of transition from just thinking about triangles to thinking about something called a unit circle. And there are two important things to realize. One thing is that with a unit circle, you use a circle whose radius is exactly 1 unit. So that's the whole point of calling this a unit circle. It's kind of like having a hypotenuse of 1 on your right triangle. The other thing that's important to realize is by using a unit circle, we can embed our triangle, or we can embed our angle inside of this big circle that you see here. And that allows us to use angles that are bigger than 90 degrees. So coming up, we'll find sines and cosines of angles that are more than 90 degrees. But for right now, let's view this as an angle sitting inside of a circle of radius 1. And there is kind of a triangle hiding here, and that's the very triangle that we like to use to compute sines and cosines. So when we take the unit circle approach, this is a more general way to think of trigonometry. We still do roughly the same thing. We draw our angle. In this case, I want the cosine of 30 degrees and the sine of 30 degrees. And then instead of focusing so much on the lengths of these sides of the triangle, we're still ultimately doing that, but we can think of it more in terms of how far over did we go and how far up did we go in order to hit this point on our circle. And in fact, what we've really done is we've created a point, and the coordinates of our point are exactly the numbers that you see here. So the x-coordinate is 0.866, the y-coordinate is 0.5, and so the idea is the x-coordinate is actually the cosine of our angle, and the y-coordinate is the sine of our angle. So the sine of 30 degrees can be thought of as the y value of this point on the circle. The cosine of 30 degrees can be thought of as the x value of this point on the circle. And you can also, if you want, think of the cosine and sine of 30 degrees as being how far over and how far up do you have to go in order to hit the point on the circle corresponding to a 30-degree angle. Now we're going to compute the cosine and sine of 60 degrees, and we're still going to do it in this context of the unit circle. So what is the cosine of 60 degrees? Well, we again think of the cosine in two ways. You can think of it either as how far over do you need to go, or you can think of it as the x value of this point up here, and we can take our pick. Keep in mind that we're in a unit circle, which means that the radius of our circle is 1. So this circle has a radius of 1. And we can see it's actually shown in the picture. How far over do we need to go? We need to go a distance of 0.5. So the x value of our point is 0.5. How far up do we need to go? That's the y value of our point. That's 0.866. And so ultimately that means that the cosine of 60 degrees is 0.5. The sine of 60 degrees, you could say 0.866, but that's just an approximation. It's probably better to say square root of 3 divided by 2. Now we're going to compute the cosine and sine of 70 degrees. And unfortunately, we don't have any fancy geometrical trick to find these distances in this picture, but fortunately the computer was happy to find the distances for us. So again, we're in a unit circle. That means that the radius of this circle is 1, and the cosine of 70 degrees is nothing more than the distance over to the right to get to our point. So that's going to be equal to 0.342. The sine of 70 degrees, that's the distance up to our point. So that's going to be 0.94. And these are just estimates. They're not exact. And keep in mind that we could also take the ordered pair point of view by thinking of this as the point, 0.342, comma, 0.94, and remembering that the cosine of our angle always gives us the x value, and the sine of our angle always gives us the y value of the point on the circle. And again, this makes sense because we're using a circle of radius 1. If we wanted to compute the cosine and sine of 80 degrees, the same kind of reasoning works. You put this picture, or you draw a picture of a circle of radius 1, and then you draw an 80-degree angle, and you think about what are the coordinates of this ordered pair. The coordinates are 0.174, comma 0.985, and that first number is the cosine of 80 degrees. So the cosine of 80 is 0.174, and the sine of 80 degrees is 0.985. And again, these are just approximations. Now, one thing that you can kind of notice is that there is still a triangle here, but that triangle is getting a little bit smaller and thinner, right? So the triangle is there, but it's getting harder to see. And what we're going to do next is we're going to make our angle even bigger. We're going to make our angle really close to 90 degrees. There's still a triangle, but it's really hard to see that thing up there. It's probably best just to think of our cosine and sine of 87 degrees in terms of the coordinates of this point. So what is this point right here? That point is the point 0.052, comma 0.999. So the idea is that the cosine of 87 is 0.052. The sine of 87 is equal to 0.999. It's really hard to see this in terms of a triangle. You sort of can think of this in terms of distances along the unit circle, right? You can at least say, well, how far up do I have to go to get to that point? I have to go a distance nearly 1. The radius of my circle is 1. It's a unit circle, so that's why my answer here is 0.999. How far to the right do I need to go? Not very far at all, only a distance of 0.05. So you can probably guess what's coming next. I'm going to change this from an 87-degree angle to a 90-degree angle, and then you can't really draw the triangle anymore, but you can still think about the sine and cosine in terms of the coordinates of the point on the circle. To find the cosine and sine of 90 degrees, we have to just draw a 90-degree angle in our unit circle, put that point up on the edge of our circle, and ask ourselves, what are the coordinates of this point? Looks to me like the x-coordinate is 0 and the y-coordinate is 1. In other words, you have to go over a distance of 0 and you have to go up a distance of 1 to get to that point. So the cosine of 90 degrees is 0 and the sine of 90 degrees is 1. And this is a pretty big generalization of what we've been doing, because we no longer have to draw a triangle. We just have to think about coordinates or distances. We can even compute sines and cosines of angles that are much bigger than 90 degrees, and it's virtually the same. There's one tiny wrinkle that's a little bit different. So it looks initially like the cosine of 120 degrees should be equal to 0.5, and the sine of 120 should be equal to 0.866. And that's nearly true, but it's not quite right. If we think about this in terms of the coordinates of this point P up here, we notice that this point is not really the point 0.5, comma 0.866. It's actually the point negative 0.5, comma 0.866. And if we wanted to think of this in terms of distances, we could say, sure, you still go up a distance of 0.866 to get to the point on the circle, but you also go left a distance of 0.5. And when you move to the left on an axis, we tend to think of that as a negative distance. And so the cosine of 120 degrees is not 0.5, it's actually negative 0.5. The sine is still positive 0.66. Upward distances we think of as positive, but downward distances are negative. Similarly, we can think about the cosine and sine of 150 degrees. We've drawn our 150-degree angle. We still have a unit circle. That means that hypotenuse, or that radius, is 1. And of course, it's tempting to say that the cosine of 150 is 0.866, which is also, of course, the square root of 3 divided by 2. And the sine of 150 is 1/2. Again, that first answer is not quite right because we have a distance that goes to the left, so we tend to think of that as a negative. and therefore the cosine of 150 is negative square root of 3 over 2. We could also think of that in terms of the coordinates of that point P. The idea is that the coordinates of P are negative square root of 3 over 2, comma, 1/2. And therefore the cosine is negative square root of 3 over 2. Now I've drawn a 180-degree angle. You can see that the coordinates of point P over here are negative 1, comma, 0. In other words, we've gone 1 unit to the left and we've gone 0 units up. That means that the cosine of 180 is equal to negative 1, and the sine of 180 is equal to 0. Something interesting happens when we draw a 200-degree angle. Again, you might be tempted to say it looks like the horizontal distance is 0.94, so the cosine of 200 might appear at first glance to be equal to 0.94, and the sine of 200 might appear at first glance to be equal to 0.342, but if we think about the coordinates of point P, it kind of gives away what's really happening. The coordinates are actually an x value of negative 0.94 and a y value of negative 0.342. And so that tells us that these two values at the top, these cosines and sines, are both negative. In other words, we have a leftward distance and we have a downward distance. Both of those should be thought of as negative. So our cosine of 200 degrees is negative 0.94. Our sine of 200 is negative 0.342. This example should now seem pretty similar. The sine of 240 degrees is going to be not square root of 3 over 2, but rather negative the square root of 3 over 2. The cosine of 240 is not going to be 1/2, but rather negative 1/2. Again, we're down in the third quadrant where our distances are left and down, and so both cosine and sine take negative values here. This reminds me of a 180-degree angle in that it's one of these angles where our point ends up right on one of the axes. So for a 270-degree angle, you just have to think about what are the coordinates of our point P. Looks like P has the coordinates 0 for x and negative 1 for y. So that tells us that the cosine of 270 is equal to 0, and the sine of 270 is equal to negative 1. So we've gone down a distance of 1, and we've not moved left or right at all, so that tells us why our cosine and sine are 0 and negative 1 respectively. It's worth mentioning that I've been talking about all these angles in terms of degrees. Mathematicians like much better to use a unit of measure called radians for angles. You can spend a lot of time thinking about why radians are a useful unit. It's related to arc length and circumference of a circle. For right now, I just want to remind you of the basic facts about radians. And the thing that's most important for me is to remember that 180 degrees is the same as what we call pi radians. So in other words, 3.14 radians, approximately 3.14 radians, is the same thing as 180 degrees. And if you know that, there's really not much else you have to think about. For instance, what's half of 180? Half of 180 is 90, and half of pi is pi halves. So for instance, if we wanted to look at this angle up here, this 90-degree angle, we could think of it as 90 degrees, or we could think of it as pi over 2 radians. Similarly, if we had something like a 60-degree angle, let's do our best to draw a 60-degree angle here. Maybe that looks something like that. So if that's 60 degrees, how does 60 degrees compare to 180 degrees? Well, 6/18 is 1/3. So it seems to me then that 60 degrees, which is a third of 180, should be the same as pi over 3 radians. Similarly, if you had something like pi over 6 radians, that would be the same as 30 degrees. Pi over 4 radians is the same as 45 degrees. 2 pi radians, that's 1 complete revolution. That's twice 180, which is 360. So it's a good idea just to play around with some of these ideas if you haven't done so in a while. The last thing I want to mention is that it's common to see mathematicians or physicists talk about the graph of a sine function or the graph of a cosine function. So this is a picture of y equals the sine of x, or f of x equals the sine of x. I just want to think about kind of how that relates to some of the computations we've been doing. So for instance, I've written a few really common angles over here, angles that we like to use a lot in trigonometry because we know the outputs of the sine and cosine function. So we know, for instance, that the sine of pi over 2, in other words, the sine of 90 degrees, we know that that's equal to 1. And the reason we know that is because we're drawing a 90-degree angle in our unit circle, and we're asking what's the y value of this point up here. And the way you see that on this picture is as follows. You go over here to an x value of pi over 2, which, by the way, that's about 1.57. And you go up a distance of 1. And what we see then is that this point up here is the point x equals pi over 2, y equals 1, and that point is on the graph of this sine function. Similarly, you could look at something like the sine of 180 degrees or the sine of pi radians. Let's do that. Let's use blue to do that. So what is the sine of pi? Pi is 180 degrees. And so that means we're looking at the point on the very left side of this picture. And that's the point x equals -1, y equals 0. So the sine of pi is equal to 0. Pi is about 3.14. So that means over here we have the point x equals about 3.14 and y equals 0. Similarly, we could look at something like the sine of 45 degrees. And if we think about that one in terms of radians, the sine of pi divided by 4, that's 45 degrees, is equal to the square root of 2 divided by 2. And the square root of 2 divided by 2 is about 0.707, and it goes on and does not repeat itself ever. So we can see that on this graph by looking at what happens when x is pi divided by 4. That's right about here. And then this point on the graph is the point, I'll draw a little arrow since it's hard to write all this in such a small space. This is the point pi divided by 4, comma, 0.707, and that's right here. And we're doing this for all sorts of different angles. And what's important to realize is that this red part of the graph is really the part where the angles of the angles that we're looking at are between 0 and 90 degrees. But all the rest of this graph is what's allowing us to, or what comes from looking at angles that are bigger than 90 degrees, less than 0. Here's an angle of 2 pi, that's 360 degrees. So by broadening our definition of what angles we're allowed to use when we compute sines and cosines, it allows us to get more than just this little tiny part of the graph. It allows us to get this entire, what we call sine wave. And studying this whole sine wave is really important when you want to study things that have behaviors that repeat, things like waves or springs that are oscillating up and down. So that's important to move beyond just the right triangle definition of trigonometry to the unit circle conception of trigonometry so that you can consider sine functions in their entirety.